All right, let's get started. So last time you saw an implementation of RISC-V processor, which was the simplest implementation we can think of in some sense. It's a single cycle. Every instruction takes exactly one cycle. But to do that, we had to assume that memory was what we call magic memory, because there is no real memory that actually functions like that. So today we'll make our processor very realistic, and what is very satisfying about this is by the time you do this lab 5, you'll be able to run all the programs you wrote in lab 4, right, on the processor you're designing, right? So there is no bigger proof than the fact that all the programs you have been writing and you can write, you'll be able to run on this. And it has a fairly extensive test bench, which is supplied by, the programs are supplied by the RISC-V Foundation, the people who actually promote RISC-V instruction set. All right, so let's get on with this non-pipeline multi-cycle processors. This is what we saw last time, right? So we have a very simple system, you know, with a PC and an instruction memory and a data memory and register file. These are the main stateful elements in our processor. And then, you know, we have some important logic inside it, a decoder and an execution unit. Execution unit essentially produces values that are needed to update the state of the system. Right? So that's how we go from one clock cycle to the next, because the value coming out of the execute are put, and you know, they're used to update register file, PC, and memory, etc. Okay, for this to function in one cycle, it's rather important that register file be able to sustain 2 reads and 1 write every clock cycle. And when that happens, we say that the reads effect takes place, not effect, reads take place before the write effect happens. In other words, you read the old values if you're simultaneously updating it, right? You read the old values from the register file. And one thing I want you to get used to, the fact that such pictures are very useful conceptually. They kind of give us an overall view of it, but you can't take them literally because there are too many arrows missing, and there may be arrows which are not exactly as I show them to be. So they are just suggestive of the data path, and I will show you some examples of where the details are not being shown, because if I drew all the details, this picture will hardly convey anything. It will get too complicated at that point, and if you build even a more complex processor, then these pictures really don't mean much. And fortunately for us, the real data path, how things are connected, is actually generated from the blue spec code you write. And the example we have been using is RISC-V, and we are just leaving out a few instructions because they are very straightforward to implement, but we just didn't want to increase the work. And these instructions all have to do with reading half word or updating the half word of memory, because our memory structure is loads and stores, and we always think in terms of words when we operate on the memory. Okay, so this is the code you saw last time, and this is true for any sequential machine we design. You know, we say make something, right? So we are making a processor in this case. Its interface is empty, which is a bit mysterious, and I'll clarify it by the end of the lecture, right? And like any module, the very first thing you think about are what are the state elements in it. And in this case, the state elements are PC, RF, IMEM, and DMEM. So you have to instantiate those. You have to make those stateful elements in the system, right? Instantiate the state, and then you have a rule, and you know, for a lack of better name, I just call it do proc. And I mean, I could have said do instruction or something. It repeatedly, the system does this rule, and the very first thing we do is we fetch an instruction from the memory. And remember, our memory is magic memory, is very simple, you know, so we immediately get the answer, you know, in the same clock cycle. And once we have the instruction, then we decode it. And once we have decoded the instruction, which is the decoder you're writing in lab 5, and once you have decoded the instruction, then the next thing you do is do the reads from the register file. So you have two sources, RS1, RS2, you go and read it from the register file, and then you have this another big combinational circuits which, given the decoded instruction and these values from the register file and the value of the PC, it tells you what are the new values that are going to be produced by this instruction, values that are needed to update the state of the machine. And finally we update it, right? So finally we go and update the state. So this is a funny procedure, funny function. You have not seen this kind of thing before last lecture. And in this, what is happening is einst executed instruction contains all the values that we need, right? And what are we updating? So we are doing something to PC, we are doing something to RF, we are doing something to DMEM, and if you see the declaration of update procedure, we don't pass the value of PC, we pass the PC itself. We pass the register file itself, we pass the data memory itself into this procedure. If you find this confusing, just do an inline substitution. Take out this procedure and put the whole body of it here, and it'll all work. Okay, yes?
How do you feed in new instructions into IMEM?
Sorry?
How do you feed in instructions into the...
Magic. It's happening in background. So we are not showing how to write the program memory at this stage, but we will preload it and start it at PC0, right? Good? All right. So these are the actions to update the state of the processor. Now let me just demystify a little bit about the hardware generation. I'm not going to give you all the details. Okay, so we have register file and we have an instruction, decoded instruction, which gives me the source fields from it. So you can imagine that the decoded instruction is coming out and there are some wires from it that connect directly to the register file. Okay, so far so good. And remember, not all instructions have RS1 and RS2. Many of them don't have RS2 because they may have an immediate operand. But there is no harm if you read it, right? Because reading something doesn't cause any side effects. You're just reading it, from the register value. But if you ever read something, if you try to use RVAL2 and it's not meaningful, then there will be problems, right? So it's the responsibility is on us, and sometimes the system will tell you, the compiler will tell you you're trying to read an undefined value, but you can write programs or the system won't be able to tell you. But the main thing to remember here is this is very common in hardware. We do things even though we may not need them. Why? Because there is no significant cost to it. Certainly it's not changing the state of the system if I do a read. Okay. Now, the interesting thing here is what happens when the same function is called from two different places. So most of the time you're going to take RVAL1, RVAL2 and feed it to the ALU. But remember our immediate instruction. There is a whole bunch of instructions where the second operand is in the instruction itself. In that case, it's something like this. That there is another bunch of wires coming out of the decoded instructions, value coming out of the decoded instruction, which has to be fed into ALU. And in hardware, whenever you have a choice, you always have a mux. And so there is going to be a mux which will decide whether you want to read the value that came out of the register file or the value that came out of directly from the decoder in that case. So I'm not showing you this kind of detail in the diagram I showed you on the previous slide because it will be too tedious, right, to draw all this stuff. So we just say, it can be done, and you really never look at these pictures, once the system gets complex enough. Let me just point out one more thing. So we have this procedure that we wrote, right, which executes instructions depending upon their type. So notice in case of op instruction and op immediate type of instructions, both of them are calling ALU, right? So the question is, how many ALUs are generated in hardware? Do we generate one ALU or two ALUs? And a little bit of analysis will show, because it's a case statement, the use of this ALU is mutually exclusive. I mean, if the first, if the ALU is being used for op instruction, then obviously it's not an op immediate instruction, right? So I should be able to use the same ALU. In fact, in this case, the compiler is smart enough to figure out one ALU will do, and it'll share it. It'll automatically put that mux I showed you on the previous slide in front of the ALU. But here is a slightly trickier case, right? So here in the load store instructions, what you see is that I'm actually computing the address. And address is an addition, right? I'm taking the rval1 and adding an immediate value to it, and our ALU does know how to do an addition. So you can ask yourself, could have I used the same ALU, right? Now, whenever you get too concerned about sharing, first thing you have to think about it, is it really a big enough thing to worry about, right? Maybe it's just cheaper to, make multiple adders as opposed to sharing an adder, because nothing is for free. If you share, then there is going to be a mux somewhere that is coming into it, etc. So this is something to think about what will happen. Now, this is the surprise here. Reuse is not necessarily a good idea, right? Let me give you the most trivial example of it. So most trivial example is obviously I'm adding 4 to PC, or I'm adding some immediate value to PC. Both are addition operations. But in hardware, adding +4 is a much simpler operation than adding an arbitrary value. That circuit will be significantly simpler. In fact, if you go back and you start thinking in terms of specialization, even though I call the ALU function here, with ALU func, but I know what ALU func is. It's going to be, whatever came out of the wire, and it's possible that it'll optimize it. It might do propagation of constants in the system. So a lot goes on in the compiling phase, which our intuition doesn't work. We have to try it out. We have to see what the system is doing with it, what is being shared, what is not being shared. So here is my advice to you. When you're designing complex digital circuits, please do not concern yourself about sharing of combinational logic, right? Because if you do that, then you are competing against what the tool will do. Tool has its own ideas, and you may have your ideas, about sharing and about, how it should be organized. This is the same kind of argument we saw earlier on in combinational circuits when we were starting with some description, right? And we wanted to think of it in terms of gates. We could do that. I mean, we could design at that level of detail, but again, the real efficiency comes from what gate library is being provided to you. And we can't keep so many things our mind. So this is layers of abstraction. Somebody else worries about, this kind of thing. In some specific case, if there is a huge combinational path, you may want to go and re-examine it. You say, did I use a good algorithm for doing add or multiply or whatever? And you saw examples of that. You had carry look ahead adder, right? Which is a distinctly superior circuit from the point of view of delay through the system. So yes, there are times when we'll worry about it, but generally speaking, when we are designing complex digital circuits, we do not worry about the complexity of combinational logic. We worry about it only after the fact. After we do synthesis, we say, how come this part is taking so much area? How come this part is running slowly, etc. So for next few lectures, no attention will be paid to sharing of combinational logic. All right, now let me move to a different class of, again, non-pipeline machines, but slightly different. And you may wonder where these names come from. Princeton architecture. The first one, I didn't give it a name, but is known as Harvard architecture, right? So Harvard, Princeton, what's the big deal here? So in the Harvard architecture, you have two different memories, program memory and data memory. In Princeton architecture, you have only one memory. Program and data both reside in it. At the time when this work was done in late 40s and early 50s, this distinction was huge. The way Harvard was doing it was not general enough. In fact, they were using completely different technology for doing the instruction memory. In fact, so much so that you could not go and modify any instruction in the thing. And one of the very big advancements in computing was because of von Neumann. He says, actually, program can itself be manipulated as data. So if we put it in the same memory, we can do loads and stores and do surgery on your program as well. So that's very cool, right? So we suddenly understood the generality of programming, but it is such a nightmare from debugging point of view that you are strongly advised never to write self-modifying code. You better have a very, very good reason where you want to do surgery on a program and produce a new program, from it. So normally we like to keep these things two separate, but I want to make a point about hardware today. So suppose they are in the same memory. If they're in the same memory, if they're like this, that instruction memory and data memory is the same box, first thing that immediately comes to my mind is, now we can no longer do memory instructions in one cycle. Why? Because first I have to fetch the instruction, do something with it, then figure out the memory operation to be performed, say a load or a store. And obviously we can't do two memory operations at the same time in the same memory. So if they are the same memory, right, and one instruction wants to first do instruction fetch, then wants to access the memory again to do some data manipulation, that is impossible to do in one cycle. Whenever you have such a situation, and this happens often, we can say it's a resource conflict. Both parts are trying to use the same memory. Such things are known as structural conflicts. You say there is a structural conflict. There is no way you can do these two things together because there is only one resource over here. So either you're doing an instruction fetch or you're doing a data access to it. And it turns out whenever you have a structural conflict, there is a systematic way of resolving it. And the solution invariably involves taking multiple cycles, right, and using some temporary storage. Why temporary storage? Because if I fetch an instruction which I'm going to execute in the next cycle, then I need some place to keep that instruction, right, from one cycle to the next. So whenever an instruction takes multiple cycles, by definition, it's always going to have some temporary storage, where the partially executed instruction is going to sit. As the processors get more complicated, there'll be so much such storage that you'll be, saying, whoa, okay.
Two questions. One is, so is structural hazard and structural conflict the same thing?
Structural hazard. Yeah, hazard and conflict is the same. I mean, I use the word interchangeably.
Okay.
Yeah.
And then I guess if you can't execute more than one memory instruction per cycle, if you put the memory together, will that slow down the speed of the processor overall?
That's a very deep question, and we're going to analyze that today. But on surface, of course, right? Because now it's going to take 2 cycles to execute the instruction. At least memory instructions are going to take 2 cycles. Previously, they were taking 1 cycle to execute. But the answer is complicated because it's conceivable that if they were separate, you could have designed faster memories, right? You could have done something. So the real answer is complicated, but at some level of cycle counting, definitely it's going to slow down things whenever you have structural conflicts. And the solution is always throw more resources at it to resolve the structural conflict. Any other questions? All right, so as I said, we need some temporary storage. So I'm going to introduce this register called F to D, fetch to decode. So I fetch the instruction, put it in this register. So now my system is very obvious. I have 2 phases in the execution of the instruction, right? The fetch phase, when I take something out of the memory, put it in F to D. And then I have the execute phase, when I take things out of F to D and execute the instruction, update everything, right? And then I'm back to doing fetch again. So that's the idea. That's how the idea of 2-cycle processor is coming about. So let's see how we would have expressed it over here. So you, of course, have storage for PC, RF, magic mem, etc. right? So this is like a refrain, and sometimes I'll write it like this, but sometimes even if I forget to write it, just know it's there, right? And you should have enough confidence to say, Arvind forgot to write it, but I know it's there. Okay, so there is this kind of state you have to instantiate, but the new state we are introducing is you have to instantiate a register to hold these instructions that you will be bringing in. And instructions are also one word size, so it's register that can hold words. All right, and the state we already showed you is just a single bit. It tells you whether it's a fetch stage or it's a execute stage, right? So the type def of this was given in the previous slide. All right, so we have two things going on, so we have two rules, right? So first rule is if state is in fetch phase or state is in the execute phase. And these are mutually exclusive. Either you are there or you are in the execute stage. So what happens in the fetch stage? Simply, if the state is fetch, then fetch the instruction and put it in F to D. That's all there is to it, right? So you can write the program, you fetch it from the memory, put it in F to D, and change the state from fetch to execute. And what happens in the execute stage? In the execute stage, you're saying if the state is execute, then instruction in F to D, and change the state to fetch. So it's like ping-ponging, right? Fetch, you fetch the instructions, it's in F to D, and once it's in F to D, you execute it, you go back to fetch. If I implement my machine like this, is it going to change the decoder? Anyone? Yes?
The decoder won't be passed R value.
Sorry?
The decoder won't get R value.
Decoder didn't need R values. Decoder was only given the instruction, it was extracting the fields, right? And produced a D-inst in that. In fact, you can figure it out. All the procedures we wrote earlier are still valid. Right, yes?
In the do fetch rule, when we set F2D to the instruction, where is the instruction coming from?
Say it again?
Where is the instruction coming from?
From the memory, I just wrote it down here. Instantiate PCRF mem. Oh, sorry, here. So fetch the instruction at PC.
So that like involves reading the memory.
Yeah. So I mean, I didn't write the code, so I'm also often going to be writing such comments, right? Hopefully it makes the slide easier to read. Yes? All right, so now let's examine what we just did again, right? So in the previous slide, what you saw is do fetch, do execute, do fetch, do execute. Now let's re-examine the this do execute rule again. And what do you see? Suppose, if you look at this, can you do decode without looking at memory, without going to memory? Can you do register fetch without going to the memory? Can you do execute without going to the memory? The answer to all those questions is yes. She says, that's interesting. The only thing I cannot do is access the memory. So maybe what I can do is I can execute all the non-memory instructions and immediately go back to fetch again, right? Just keep doing it in the same cycle, in one cycle. Fetch the instruction, decode, blah, 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 right? Fetch, fetch. But on the other hand, if it's a memory instruction, then I have to wait, right? Then I have to go and fetch it, and I can't start the fetch because I have just fetched something from the system. So the thing is, execution of all the instructions except the load and store instruction could be completed in the fetch cycle itself because there was no structural hazard. Structural hazard was only for memory instructions. So how can I exploit this idea? How can I make it? How can I use it to my advantage? The advantage I'm looking for is this, that all the non-memory instructions I want to execute in one cycle. And for memory instructions, okay, I'll take 2 cycles, because I have no choice. I have a structural hazard in that case. So instead of executing every instruction in 2 cycles, I want to execute most of them in 1 cycle and some of them in 2 cycles. Can I modify my processor to do that? So let's look at this picture again where you had this. So if I'm going to execute everything, right, as soon as it comes out of the memory except for load store instructions, then I don't need F to D because I don't have to store the instruction. So I can take this out, and then, for a memory instruction, I say if it's a memory instruction, then please store the partially executed instruction because execution has done something. Put it all in another register which I'm calling E to M, execute to M register. So after execute, whatever comes out, you're going to put in this register. And in the next cycle, you will do the memory operation and go and update things at that point. Is this high-level idea clear to everybody? That we were, until now, fetching something from the memory, taking our time. In the next cycle, we executed the instruction we had fetched. Now we are being much more aggressive. We fetch the instruction, we ask the question, are you load store instruction? That question itself cannot be asked unless you have decoded it, right? If it is not a load or store instruction, you say, okay, just execute it. Update the register file, do everything, and go and do the next fetch. On the other hand, if it is a load or store instruction, then say, oops, it's going to take another cycle. So whatever values I have computed, I'm going to put into another register called F to D, right? Its size is different, because it has executed instruction in it, partially executed instruction in it. And then in the next cycle, I'll go and consult the memory. There was a question. All right. So the data path shown here is very, very approximate, so I'm not showing muxes and many other things. And so don't worry about that. Okay. Let's look at the code. So what I did is I took the single cycle processor code and I wrote down everything I need for non-memory instructions, right? I just take something, I decode it, I fetch the instruction, decode it, I execute it after doing the register fetch, etc. And assuming it's not a memory instruction, then I can go and update the register file and update the PC, and I'm ready, I can go again. On the other hand, somewhere I have to check what if it is a load store instruction. So that's what this red stuff is. Suppose it is a load store instruction. If load is, if it's a load type or a store type, then what do? Then you put the executed instruction, the data you had computed, in this register temporarily, right? And you change the state to memory access, right? Because now we need another rule where we'll do the memory access to it. So this instruction is not done yet, and you will go here in the next rule shown at the bottom, which is saying this rule executes only when the state is memory access. And what do you do in that? You will get something from the memory, and you will go and execute it at that point, right? Which was all happening inside the update part. I could have spelled it out more, but I didn't. If you really want to understand it, go and open up update procedure and put everything in and see what happens in there. Okay, so what have we done? Why are we so happy now? Why is this new processor, this another Princeton processor, better? Let's try to quantify it a little bit. What are the performance implications of it? Right? Suppose fraction f of unexecuted instructions are memory access instructions. Then 2-cycle Princeton, the first one I showed you, is always going to take 2 n cycles, right? You are executing n instruction, every instruction takes n cycles, so it takes 2 n cycles. On the other hand, if you have this variable cycle Princeton processor, you will have f number of instructions because they are memory instructions, so they take 2 cycles. But the rest of the instructions, 1 minus f instructions, only take 1 cycle. So you can do the simple arithmetic, and you can see that 1 minus f times n is certainly less than 2. because f is a fraction of 1 over here. Do you have any idea what f is? What fraction of instructions are load store instructions? Dynamically, right? If your program executes 1 billion instructions, how many do you expect to be load or store instruction? So you may not have experience yet, yes?
I would guess about 30-ish%.
It could be 30%, but it's somewhere between 50 to 30%, but it can vary a lot depending on what program you are running. But I think 30% is a little bit on the high side, but not a bad number. Okay. So basically the reason why that number is important is it tells you that we are winning. If we could do this, now when I say winning, we are winning in terms of cycle count. This machine is going to take fewer cycles to do the same program. Okay. However, cycle count is not the whole story as far as the performance is concerned, and we will come back to this topic later on in the course. All right. So now we are good. We have a computer. It's not realistic enough because the memory is not right. When we have a large memory, it's not going to be magical. It's not going to be you read it and you instantly get an answer, from it. It's going to be a request response system. You give it a request and little later you will get a response from it. If you are lucky, maybe in the next clock cycle, right? But it may take, many clock cycles depending upon the memory technology. We'll be hearing a lot more about it in the next lecture. Sorry, not in the, next lecture. So if realistic memory has to look like this, you submit a request and later on you can request the answer. You say, have you gotten an answer? If you have an answer, then I can proceed with it. In other words, instead of instantaneous, there is a gap. Make a request, little later you get an answer from it. That's the realistic system. Okay. And we'll assume stores generate no response because store is just doing a side effect on this module, on this memory module. It goes inside and does something. It updates some word inside it. So the interface for the memory is simply two procedures. Okay, it's an action method, which is a request, which goes, you are submitting a request to it, and then response method, which is an action value method because it also returns some value, right? Value will be word type again over here, and that is so there are these two operations that are going on. And because all load stores, everything is going the same way, we have to come up with a data structure so that we can feed it. And that's what is being shown here, that this is what it looks like. So you have a memory op, which can be load or store, and you have to give me an address. And if it's a store, then you also have to give me the data. So how do I invoke it? So if I'm making a load request, it'll look like this, and there is no data in it. So I put a question mark. If it's a store, then I do this, and I also supply a piece of data. So two kinds of requests can go in, and depending upon what kind of request it is, they have slightly different amount of information in the data structure itself. And then how do I process the request, response from it? I can just say this is my memory and give me the response, and whenever the response is ready, remember everything is guarded. You're not going to get this response until the memory has the response, with it, and then it's returning a piece of data. Because for stores, there is no response that we get back here. It'll be void of some sort. Everybody understands this structure, right? This is our memory structure. Realistic memory, request response memory. This abstracts all kinds of crazy things we can do inside the memory system, and believe me, we're going to do crazy things inside the memory system, right? That's what next week is about. Because designing memory systems is as difficult, as complicated as designing processors. So you must understand both if you're going to design a good system, all right? But today's lecture is about processors. So let's understand the processor. So in my realistic system, I have replaced that magic memory with request response memory. Now, this picture tells you something, but certainly not the whole story, because now the problem is, what were we doing in fetch earlier? We were fetching something, putting in F to D, or working on it, right? We can't do that. Now, first we request something from the memory, then we have to execute another rule where we'll wait for the response, because the response is not instantaneous. So in general, it's going to take time, to do that. So how to express such an idea? And this is what we do. So now we're going to make processor, which is also multi-cycle Princeton processor. We can instantiate the registers, etc., or everything we need, right? Whatever we need, you're very good at it by now, right? You have seen it so many times in previous slides. Now, first instruction is fetch. What is fetch going to do? It's going to send a request to the memory, right? That's what it says. Initiate instruction fetch. And once you have done that, you say, okay, now go to the execute cycle. And what does execute do? So execute is going to wait until it gets a response from the memory, right? And once it has that instruction, now it can merely go and decode, do the register files, etc. It can do even the execution, but what it cannot do is do the memory instructions, right? Because there's that structural problem again in this. So we can, but on the other hand, we can initiate the memory instruction if we want, right? Because remember, we had initiated it in the fetch stage. In this rule, we are waiting for the response. As soon as we get a response, if we want, we can initiate another thing. But we will be initiating this only if it is a memory instruction. If it is not a memory instruction, then you just go back to fetch. So for all non-memory instructions, initiate the fetch, something comes back from memory, you go and decode it, execute it, and you go back to fetch. Right? So this is the cycle. But the moment you detect a memory instruction, you start another fetch. I mean, not fetch, another operation on the memory. And now once you do that, then you have to wait for it. So you have started the fetch, but if it was a load instruction, you know that data from the memory is going to take a while to come back. So there is a separate rule. This is do load wait. It's just waiting for the answer that is coming back from the memory. And once you get the answer back, then you're again in good shape. You can, process everything and go back to fetch again. Is this point clear to everyone? That previously, in our single cycle machine, we fetched the instruction, it was instantaneous, so we executed it, fetched it again, right? Except for memory instructions. Now, even for ordinary instructions, we start a fetch, we wait for the answer, then we execute it, go back to fetch, right? So 2 cycles is the minimum that any instruction will take here. And if it's a memory instruction, then it will take yet another cycle, because we have to wait. Yes?
But why is there conditional statement inside of like a free tool?
So you tell me.
Is it like a guard?
No. Guard is associated either with a method or with a rule, right? When you are writing the body of something, right, the guards are all implicit. You don't write guards explicitly, but you can have a conditional. So you have decoded the instruction, right? Because you have the instruction in your hand now. You're talking of this thing over here. So you have in this thing, you're waiting for the instruction to come back, and once the instruction comes back, then you, if it is not a memory instruction, how do I know it's not a memory instruction? Because I have the decoded instruction in my hand. And I can ask the question, are you a load or a store, right? Say, no, I'm neither. If I'm neither, then I go everything else and go back to fetch.
I guess, I was asking a syntax question. Like, why does it say do fetch, for instance, starting from the state equals fetch?
That's the guard. Do fetch can only happen when the state equals fetch.
Why don't you need an if?
Well, for that you have to go back to lecture number 5 or 4 or 3, something like that. Because we did guards long time ago, right? Any other question? Yes?
Where is the instruction actually getting decoded?
Sorry?
Where is the instruction actually getting decoded? Is that the same time when you take it from the
Yes, I should have written more details here. So I think, when you're in this state, you are getting the instruction, and once you have the instruction in your hand, then you can decode, you can do register fetch, you can do execute, everything the moment you have the instruction. You're doing all that.
So is there some other rule that exists for like the actual memory module that is like telling, because wouldn't you execute, you need to have like another guard that says like memory is ready or something?
You have to have something, like the one I showed you earlier in the previous slide, that you have a memory module. So once you initiate, you're only initiating the memory load operation here. You have to have another rule which waits for the results to come back from the memory, which was shown earlier, right? The slide. Yes?
So it looks like you're only going to load the after you're like executing the instruction. But don't you also have to wait when you're trying to fetch something, fetch an instruction from memory?
No, you're absolutely right. I'm sorry, I should have written here more explicitly. When you do execute, the state has to be execute, but you're also waiting for the instruction to come back from the memory. I should have written that line, right? So you're waiting for the instruction to come back. So even if you're in the execute stage, if the memory doesn't give you an instruction, you can't proceed at that point. You'll just be stuck at that stage. Yes?
Are you stuck in that state all within the same clock cycle? Or are you cycling while you're sitting there waiting?
Very good question. So is there any guarantee that when state equals execute, the instruction is available? There is no such guarantee. I mean, that depends on your memory design. And that's the beauty of this kind of system, right? It's resilient to, regardless of how long it takes, for the memory to respond. This rule can fire only when the data is available. That's coming because of ready signals and, enable signals, etc. So you are always waiting for all the guards implicitly. And one of the guards here is for the get from memory instruction. Yes?
I guess I'm confused. Do fetch. Why do you want to go to execute instead of load wait?
Because you're fetching an instruction, you're not doing a memory instruction. You're doing a general instruction. You don't know what it is yet.
Every clock cycle, you have to wait anyway for the instruction. So why not just have everything go through that loop?
That's exactly what's happening. We have to fetch an instruction every time, right? But if we are not done processing the previous instruction, then there is no point in starting the next fetch, right? So you are fetching, you're trying to execute it. As soon as you're done executing, you go back to fetch. But sometimes while executing, you discover it's a memory instruction. So now you have to initiate another thing. Say, oh, please read the memory again. And you will need another rule which waits, for it, from it. And then once you have the load value, then you can again go back. I have deliberately not given you more details of this because that's what I want you to figure out in the lab. Right? So you'll be writing the code, and believe me, by the time you're done with this lab, you would understand it. You would know exactly. And another wonderful aspect, as I told you, of doing this is all the programs you wrote in lab 4, right, will run on this processor at that point. So you would have built a general purpose RISC-V processor, which is almost like the simplest RISC-V processor. We simplified it just a little bit by omitting half-word instructions. Okay, now there is another interesting thing that happens. Until now, we have looked at very simple ALUs, right, in which everything was combinational. But once you get to very complex operations like floating point, it can't be done in one cycle. It takes many, many cycles to do a floating point operation. Or if you wanted to build an accelerator, suppose you say, I'm in love with GCD, I would like to have an instruction that does GCD. Well, GCD also can't happen in one instruction, right? Sorry, in one cycle. So this is almost like saying the same thing, that just as if it was a memory instruction, I initiated it and then I wait for it. If I come across an instruction which takes many cycles, I will initiate it and then I will wait for it, right? And that's exactly, what is shown here. So if it's a fetch stage, initiate instruction fetch, go to execute, and execute all instructions except memory instructions and multi-cycle instructions, and go to fetch, because all those things can be done in 2 cycles. If it is a memory instruction, then you will initiate the memory operation and go to memory wait operation. If it's a multi-cycle operation, initiate the multi-cycle operation and then go to wait for the multi-cycle operation. So does everybody see that? Fetch, you come to execute. In the best case, you immediately go back to fetch. In the load store case, you will go and initiate a load store instruction and wait for the result of the load. For multi-cycle operation, you will initiate the multi-cycle operation and wait, for the result for that instruction to be completed. And that's what this thing is. And of course, this is also lab 6. You'll be doing all this. So lab 6, you're going to write the decoder, and you're going to write the lab 5, sorry. You're going to write the decoder, and you're going to write these multi-cycle implementations. What my goal here is to teach you the generality of it, right? You should be able to deal with multi-cycle things. If something is taking too long, break it down, right? Make it request response so that it remains, latency insensitive in some sense, or oblivious to how long operations take. And the framework we are providing here in terms of atomic rules and doing it like this is extremely general. You can express many different architectures very simply in this manner. I want to do one more thing before we stop, and that is do a very, very crude analysis of timing in this. So let's look at single cycle implementation. What all do you have to do in one clock cycle in that? You have to do an instruction fetch, that is TM, right? You have to do decoding, that's T decode. You have to do register fetch, that's TRF. Right? You have to do ALU because there is some ALU operation. You may have to, if it's a load store instruction, you're also going to the memory, etc. Right? And then you have to write back. All these operations, propagation delays of all these things is additive. Your clock cycle has to be large enough to accommodate all these propagation delays. And that's actually problematic because memory time is usually the dominant factor. Memory takes a long time. Anytime you go to the memory, it can take more than a cycle or 2. And here in one clock cycle, you're going to 2 memories. You could do that because they were separate memories. But that's besides the point. The main point is that if it's all happening in one cycle, there are 2 sequential memory operations going on here. So this is the amount of time it'll take. And if you look at my 2-cycle implementation, then immediately you will discover that it's something like this. This is again approximate. I'm taking out the time to access the memory the second time out of it. Because if you were going to the memory again, I broke it down. I took it out in a different rule. So now the propagation delay in this system is actually 1 less memory. You may want to adjust it by adding some more RF or this and that, or R right actually I need probably in this. But you should be able to get the high level point that the biggest difference between the single cycle one and multi-cycle one is that this is going to take 1 less memory delay in it, and therefore potentially this clock cycle can be much, much faster. Much, much faster. If you imagine that memory cycle is the dominant thing in this clock, determining the clock cycle, then you're essentially saying maybe my clock can go twice as fast if I break it down into 2 cycle operations. But that doesn't mean that your machine is going to run twice as fast even though your clock is running faster. Because why? Because now instructions are taking longer. Some instructions are going to take 2 cycles. Some instructions are going to take 1 cycle. So you can start seeing that even in this simpler design, to do the real analysis of how long your program will take to execute is very dependent on the program because of what kind of instruction mix it has. And it will depend upon many other implementation details which we haven't discussed. For example, how is memory going to be done? Right? How is memory going to be implemented? Okay, so this is just one more thing I want to say, because this will also affect the lab. It's a bit of a mystery that you have a processor and its interface is empty. Say, really? It's like a black hole? Right? It does something very happily, but nobody else can see what it does, because the thing I've been preaching is that we can only affect a machine through its. So we are cheating a little bit. The way we are cheating in this is for processor designs is, for testing, processors are always connected to some other processor, right? Because this is the design you're doing. And so what we can do is this other processor by some magic goes and loads the memory of the processor you are designing, sets the PC to 0, now it gets going. How do we know it has ended? Because when it stops, it goes and writes in a particular location in the memory, which I'm always watching. I'm saying, somebody wrote it, they're done. Simulation stops the moment somebody writes into that location. And that's the kind of interface you will be using in the lab all the time, right? So it always starts at PC 0, program is always preloaded, so I haven't given you the capability of being able to load the program in your system, and when the program terminates, it writes a 0 in a predetermined location and the simulation stops. Now the only other thing we have to deal with is if there is an illegal something that happens, unusual stop. So even in that case, we can just stop the simulation, we can do something inside it. And these are all ad hoc conventions. And there is a particular one being used, which is specified very clearly at the beginning of Lab 5 handout. So please spend time, doing Lab 5. And anything you don't understand, recitations are there, all of us are there to help you with that. But it's a very, very important lab for you to understand how programmable hardware works. Thank you.